Hello, this is the first video for Graphs and Networks 1, Definitions and Modelling, for OCR Discrete AS Further Maths. This provides an introduction to graph theory. Two strands of mathematics, graph theory and topology, developed separately, so there are two sets of vocabulary or terminology which may be interchanged. This is just something to accept and deal with. Graphs you have met in your maths to date have tended to be two-dimensional, with axes, for example, x and y. In graph theory, a graph is given a broader definition as a mathematical structure used to model relationships. Thus, it may just be a diagram made up of dots and lines to show relationships between discrete sets of objects. It does not have to be geographically accurate, even if it represents a map. Graphs are good for modelling problems or situations where there are connections, and this is the main information conveyed. We've already talked about relationships, but they can also be used for tasking resources such as staff, for route maps, for utilities networks, or for autoroute or navigation systems. Here is an example of a graph which you may be familiar with, the London Underground. The routes and connections between the stops are shown, but the distances are not accurate. You need to be familiar with the terminology used in graph theory. For example, a graph is a series of nodes or vertices connected by edges or arcs. A network is a weighted graph where each arc is associated with a number. Generally, a network shows a simplified version of a real-world situation or information, and the weights given can represent cost, time, number of passengers on a route, distance, and so on. To find the degree or order of valency of a vertex, we count how many edges attach to the vertex. So, for example, here, this node or vertex is of degree 1. This node is of degree or order 4, while this one here at the bottom is of degree, order or valency 2. In a connected graph, it is possible to go from any vertex to any other vertex, even if you have to go via other nodes. In a graph which is not connected, you can see that there is no arc linking this portion of the graph or subgraph to this other portion. So what would a graph with 6 vertices of orders 1, 1, 2, 3, 4, 4 look like? You may wish to pause here and try and draw one for yourself. Here I have sketched one of 5 vertices with orders 1, 2, 3, 4, 4. So I just need to add another node of order 1 to complete the graph. But I'm having problems. If I added another vertex of degree 1 to join to the node of order 4, that would obviously then become a node of order 5. Similarly, if I try and join another one to the vertex of degree 1, that then would become a 2. I just can't find a way of doing this. Interestingly, if I add the numbers 1, 1, 2, 3, 4, 4, I get an odd number. Let's explore this further. If we discuss how many edges there might be in a graph with vertices of order 1, 1, 2, 2, 2, 4, then we could of course draw a graph and count them, or we could stop and think about it logically. If we add those numbers up, we get a total order of 12. But then each arc will have been counted twice. So therefore, it would indicate that there are actually 6 edges or arcs in that graph. So you may wish to pause now to try and draw a graph or two with those orders for yourself. Well, I managed to draw some graphs for these orders. So here are 2 examples, one a connected graph and the other not connected. If you count the edges in both of them, you will see that there are 6 edges, which as we expected is half the total order for the graph. For terminology, we can see that a subgraph is simply part of a graph, and a loop is an edge that starts and finishes at the same vertex. A simple graph does not have any loops or more than one edge connecting any pair of vertices. You can see here an example with some pairs of vertices connected by two edges. A complete graph is a simple graph in which every pair of nodes is connected by an arc. We use the notation Kn to show the complete graph with n vertices. To answer the question how many arcs in K4, you may wish to pause and draw this for yourselves. As you can see, each of the four nodes is connected to each of the others, so therefore you would expect order of 12 and therefore 6 arcs. You can also just count the arcs up, so 4 around the edges and then the 2 diagonals. If you look at K2 and K3 as well, you will see that there is a pattern emerging. You may wish to pause and see if you can work out what K5 and K6 would be like. So, for Kn, we would find we were summing 1 up to n-1. So the number of arcs will be n/2 times n-1. You may also wish to think of this as Cn2 or n2 and link it to your work on series and combinations. This makes sense because every vertex is connected with every other vertex, i.e. you have n nodes of n-1 arcs, but then every arc is counted twice. A digraph or directed graph is one at which at least one edge has a direction associated with it, shown by the arrows, and hence they have both in-degree and out-degree labels. A bipartite graph is a graph where the nodes are in two distinct sets, on the right and left. Each edge connects a member of the first set to a member of the second set. We can make this a complete bipartite graph, K43, by adding more edges. So, if we think about the fact that the four nodes in the first set each have 3 arcs going to each node in the second set, altogether there would be 12 arcs. So K43 will have 12 arcs. And Kmn would have m times n arcs. We can say that 2 or more graphs are isomorphic if they can be stretched, twisted or otherwise distorted or morphed into each other by labelling their nodes so the linking arcs are the same. These 3 examples here, we can see that they each have 5 nodes. Let's have a look at the orders. So that's a 1, a 3, a 3, a 2 and a 3. Here we have a 3, a 2, a 3, a 2 and a 2. Here we have a 3, a 2, a 3, a 3 and a 1. So, although they all have 5 nodes, we can see that graphs 1 and 3 have a 1, 2 and then 3 3s, whereas the graph in the middle does not. Therefore, the only ones that might possibly be the same graph are graphs 1 and 3. The same degree sequence, or ordered list of vertex degrees, is necessary but not sufficient to show isomorphism. So how would we check if 2 graphs were isomorphic? Well, we might use an instance or adjacency matrix. Let's look at this graph here. If we label the nodes A, B, C, D and E, we can complete a matrix to show the relationship. A does not have any loops, nor does B, C or D. E does have a loop, and it's given a 2. A connects to B with 2 arcs, but not directly to C, D, or E. You'll notice that there is some symmetry in this matrix. So B connects to C and D, but not directly to E. C connects to D and to E. And D connects to E. But we will notice that it is a digraph, and therefore we'd have to be careful about direction. So let's just see how a graph can actually change but still be isomorphic. So we can move node D and node B, but they are actually still exactly the same graph. And we could check this by looking at their incidence or adjacency matrix, which should be exactly the same. Further vocabulary that you need to know is that a route can be a walk, a trail, or a path, and may be closed. So a walk is a set of arcs where the end vertex of one is the start vertex of the next. Nodes can be revisited. So for example, I could go from A to E to D to C, back to E, and then on to, say, B. A trail is a walk in which no arcs are repeated. So A, B, E, D, C, with nothing repeated. A path is a trail in which no nodes are repeated, so I cannot revisit, for example, C. And a cycle is a closed path. So here I would be perhaps going from A to B to E and back to A. That would be a closed path. We will be using this vocabulary, especially the idea of a cycle, in later videos. A tree is a simple connected graph with no cycles. For example, this one here. A spanning tree of a graph G is a subgraph which contains all the vertices or nodes of G and is also a tree. For example, here we have a graph, and by taking out 2 arcs, we manage to find a possible spanning tree. Note that every tree will have one more node than the number of arcs, as it is connected. But there are no unnecessary arcs used because there are no cycles or loops. So for example, if we were to ask how many arcs are there in a tree with 10 nodes, the answer would be 10 minus 1 or 9. If we were to consider a simple connected graph G with 8 vertices, then the minimum number of edges that G could have would be 8 minus 1 is 7. But the maximum number of edges that G could have would be if it was a connected complete graph, which would be K8. So half of 8 times 7 equals 56. Half of 56 would be 28. In the next session 1.2, we will look at modelling with graphs and networks.